Back in 2008, a small British company called Ariel unveiled something completely insane. They dropped a compact, Hartley-built V8 derived from Suzuki Hayabusa motorcycle engine architecture into a car that weighed less than a grand piano. The Ariel Atom 500 was rated at roughly 500 horsepower from a 3-liter engine that weighed just 90 kilograms. It could hit 100 kilometers per hour in under 2.3 seconds and had a power-to-weight ratio of 909 horsepower per ton. For context, a Bugatti Veyron sits at around 530, so if motorcycle engines are this absurdly capable, why doesn't every car manufacturer just use them? That question sounds simple. The answer is one of the wildest engineering rabbit holes you will ever go down. By the end of this video, I am going to show you a single number that completely changes how you think about the bike versus car engine debate. Let's start with the raw numbers, because they are honestly a little embarrassing for the car world. The Honda CBR1000RR-R Fireblade makes 218 horsepower from 999 cubic centimeters of displacement. That works out to 218 horsepower per liter. It is naturally aspirated, just breathing regular air from the street. The BMW S1000RR hits 205 horsepower per liter. The Kawasaki ZX-10R manages 203. The Ducati Panigale V4R reaches 218. And with the racing exhaust kit installed, it pushes past 237 horsepower per liter. Again, no turbo, no supercharger, nothing forced. Now compare that to cars. A Toyota Corolla's 2-liter engine produces about 84 horsepower per liter. A Suzuki Breeza manages around 70 horsepower per liter from its 1,462 cubic centimeter 4-cylinder engine. Even something like a Ferrari 488 GTB, with its twin-turbo V8, only hits about 172 horsepower per liter. One of the most impressive mainstream examples is the Mercedes-AMG A45S. It needed a turbocharged 2-liter engine running insane boost pressures to hit 211 horsepower per liter. Sport bikes have been casually doing that number for years without forced induction, and while costing a fraction of the price. And if you want to see what happens when motorcycle engineers do add forced induction, look at the Kawasaki Ninja H2R. Its supercharged 998 cubic centimeter inline 4 produces 326 horsepower. That is 326 horsepower per liter from a single liter of displacement. That kind of number puts it in the same power density conversation as Formula One-derived hypercars. So, what's going on? How does a motorcycle engine squeeze 2 to 3 times more power from every cubic centimeter? There's a formula that explains everything, and it is beautifully simple. Power equals torque multiplied by RPM. That's it. That's the entire skeleton key to this story. The BMW S1000RR produces a modest 83 pound-feet of torque. A regular Honda Accord makes more than that, but the S1000RR delivers that torque at 13,000 RPM. A 4-cylinder engine spinning at 13,500 RPM fires 27,000 power strokes per minute. That's roughly double the combustion events compared to a car engine cruising at 6,600 RPM. Twice the explosions per minute means roughly twice the power extraction from the same amount of displacement. But here's the obvious follow-up. If revving higher is the answer, why can't car engines just rev higher too? The answer lives inside a concept called mean piston speed. Every time a piston goes up and down inside a cylinder, the metal surfaces are scraping, heating, and absorbing violent forces. There is a practical ceiling for this, generally put somewhere in the mid-20s meters per second for most production engines. Push significantly beyond that, and things start to come apart. Both car engines and motorcycle engines approach the same 25 meters per second ceiling. The difference is how they get there. The Honda Fireblade has a bore of 81 millimeters and a stroke of just 48.5 millimeters. At 14,000 revolutions per minute, its piston speed hits 22.6 meters per second, still within the range that modern superbike engineers are willing to live with. Now take the Toyota Corolla. Its engine has a bore of 80.5 millimeters, almost identical to the Honda sport bike, but a stroke of 97.6 millimeters. That long stroke hits 21.5 meters per second at just 6,600 revolutions per minute. Same physical limit, dramatically different engine speeds. This is why bore-to-stroke ratio matters so much. Think of it this way. Imagine two runners on a track. One takes long, loping strides, the other takes short, quick steps. Both cover the same ground speed, but the short stepper can increase their cadence much further before their legs give out. That is exactly what happens inside these engines. Every modern leader-class superbike uses an over-square configuration where the cylinder bore is much wider than the piston stroke. The Fireblade's ratio is 1.67 to 1. The Ducati Panigale 5 sits at 1.67 to 1 as well. BMW S1000RR comes in at 1.61 to 1. The Yamaha R1 is at 1.55 to 1. And the Kawasaki ZX-10R, interestingly, runs a slightly less aggressive 1.38 to 1, but compensates with other valve train tricks we will get to in a minute. Car engines do the opposite. The Corolla's ratio is 0.82 to 1. It is under square, prioritizing low engine speed torque and fuel efficiency over high engine speed power. That big wide bore gives motorcycle engineers another massive advantage. More room across the top of the cylinder means space for larger intake valves. The Fireblade runs 32.5mm intake valves, and BMW S1000RR pushes even further with 33.5mm intake valves, among the largest in the 1,000 cubic centimeter Supersport class. Bigger valves let more air rush in at high revolutions per minute, and more air means more fuel can burn, which means more power. But making an engine spin at 14,000 RPM creates a brutal engineering problem that does not get nearly enough attention. Inertial forces on engine components increase with the square of RPM. Double the engine speed and forces do not just double, they quadruple. In a representative high-performance valve train at 12,000 RPM, each steel valve can experience around 26 pounds of inertial force per cycle. Multiply that across 4 valves per cylinder and 4 cylinders, and you are talking about hundreds of pounds of force slamming back and forth inside the engine every fraction of a second. The solution is obsessive weight reduction of every moving part inside the engine. Titanium valves weigh 35 to 42% less than equivalent steel valves. In real terms, swapping a 33-gram steel valve for an 18-gram titanium, 1 drops the inertial force from 26 pounds to about 14 pounds per cycle. That single material change can buy several hundred RPM of additional safe rev headroom with 0 other modifications. The BMW S1000RR uses hollow-bored titanium intake and exhaust valves. Ducati's high-end models have used titanium intake valves costing roughly $700 each. And this obsession scales to every reciprocating component. When BMW built the M1000RR, their homologation special, they upgraded from forged steel connecting rods weighing 334 grams each to Pankel titanium, connecting rods that were 85 grams lighter. As part of the M1000RR's broader high RPM package, the red line climbed from 14,600 to 15,100 RPM with improved power across the entire upper rev range. The Ducati Panigale V4R takes it even further. Its titanium connecting rods are gun-drilled with a tiny 1.6mm hole running the entire length, allowing oil to flow from the big end to the small end bearing. It was the first production road bike to use this technique. The Yamaha R1 uses fracture-split titanium con rods, drawing on learnings from Yamaha's YZR M1 MotoGP program. Diamond-like carbon coatings, abbreviated DLC, reduce friction across the entire valve train. Honda claims a 35% reduction in friction from DLC-coated camshafts on the Fireblade. It was their first production motorcycle to use this technology. Academic studies have measured friction reductions exceeding 45% at the cam follower interface with DLC. The coefficient of friction drops from 0.6 or 0.8 on bare metal to as low as 0.05. DLC coatings are now standard across top-tier leader-class superbikes. Now, even with ultralight materials and space-age coatings, there is still a fundamental problem at extreme engine speeds. It is called valve float. When an engine spins fast enough that the valve spring cannot pull the valve closed before the camshaft comes around again, the valve floats. It can hang open in the combustion chamber. In an interference engine, which every sport bike uses, a floating valve will collide with the piston. When that happens, you are looking at a destroyed engine. Engineers developed 3 different technologies to fight valve float, and each one is fascinating. Ducati took the most radical approach with their desmodromic valve train. Instead of using springs to close the valves, Ducati uses a second cam lobe and a second rocker arm that mechanically pulls each valve shut. With no spring, there is no spring-induced float, period. Engineer Fabio Taglioni designed the first desmodromic engine in 1956, and Ducati brought it to production motorcycles by 1968. The current Panigale V4R exploits this system to reach a class-leading 16,500 revolutions per minute redline, the highest of any production leader bike. The downside is cost and complexity, with valve service running $800 to $1,000 and service intervals of around 15,000 to 18,000 miles. In MotoGP racing, teams went further with pneumatic valve springs. Instead of metal coils, compressed nitrogen acts on a sealed piston and cylinder arrangement to return each valve. The gas provides a progressive return force with zero resonance. Metal springs have natural harmonic frequencies that can cause destructive surging at certain engine speeds. Nitrogen does not care. Renault pioneered this for Formula One back in 1986, and every Formula One engine adopted it within a decade. Aprilia brought it to MotoGP in 2002, with Honda and Yamaha following by 2007 and 2008. The result is MotoGP engines revving to 18,000 and even 19,500 revolutions per minute. Yamaha reported a 40% reduction in valve train weight after switching, but the system needs an onboard compressor, a reservoir pressurized to 200 to 300 bar, and a precision regulator. It is far too complex and expensive for any production bike. The technology that actually made it to your local dealership is the finger follower. This small forged rocker arm pivots between the camshaft and the valve, replacing the heavier bucket and shim design that older sport bikes used. Kawasaki's ZX-10R project leader reported a roughly 20% reduction in reciprocating mass. The Suzuki GSX R1000's finger follower weighs just 10 grams, with an effective moving mass of only 3 grams thanks to the pivot point. By 2020, every major sport bike manufacturer had adopted this technology, which migrated from Formula One through MotoGP and into the production bikes you can actually buy. If you are enjoying this deep dive into motorcycle engineering, hit subscribe. We cover this kind of technical content every week. Beyond the internals, motorcycle engines have a massive packaging advantage that cars simply cannot replicate. A Yamaha R1 engine, including its integrated gearbox and clutch, weighs roughly 59 kilograms. A comparably powerful car engine alone weighs 130 to 180 kilograms, and that is before you add another 50 to 80 kilograms for the separate transmission. The motorcycle powertrain achieves roughly 3 times the power-to-weight ratio as a complete system. Motorcycle engine blocks are high-pressure die-cast aluminum alloy, with magnesium used extensively for covers and casings. Magnesium's density is just 1.74 grams per cubic centimeter versus 2.7 for aluminum and 7.2 for cast iron. Many car engines, especially diesels and larger displacement V8 engines, still use gray cast iron blocks because it handles sustained high temperatures better and costs far less. But it weighs nearly 3 times more than aluminum per unit of volume. Inside the cylinder bores, most sport bikes use Nickel, a nickel silicon carbide electroplated coating originally developed by Mahle in 1967. This provides a surface hardness of roughly 69 to 72 on the Rockwell C scale, which is harder than most drill bits, while eliminating the need for heavy iron cylinder liners entirely. It is one of those invisible technologies that shaves weight from a place you would never think to look. And the motorcycle gearbox uses dog engagement instead of the synchromesh system in cars. Metal teeth slot directly into matching openings with no synchronizer rings, blocker rings, or friction cones. It is simpler, lighter, and faster. Modern quick shifters exploit this design by having a sensor detect shift force, at which point the ECU cuts ignition for 40 to 60 milliseconds, unloading the gear dogs so they slide into the next engagement. Shift time drops to about 50 milliseconds versus 200 to 500 milliseconds for a car manual. It is brutal, it is loud, and it is unacceptably harsh for a car. But on a bike, it is perfect. There is one more hidden advantage that almost nobody talks about, and it has nothing to do with engineering. It is regulation. Under BS6 and Euro 5 emission standards, motorcycle emission control systems only need to demonstrate compliance for 35,000 kilometers. Cars must maintain compliance for 160,000 kilometers, and under Euro 7, that extends to 200,000 kilometers. That is a 4.6 to 1 durability gap. This single regulatory difference cascades through every engineering choice. Car manufacturers must tune conservatively so that catalytic converters and exhaust treatment systems remain effective through 160,000 kilometers of degradation. Euro standards specify deterioration factors of 1.5 times for carbon monoxide and 1.6 times for nitrogen oxides, meaning the calibration must account for equipment that is 50 to 60% less effective at end of life. Motorcycle durability requirements are much shorter, which gives engineers significantly more room to optimize for performance. Their catalysts are smaller and lighter. Onboard diagnostics arrive significantly later on motorcycles than on passenger cars. This regulatory asymmetry is a hidden enabler of motorcycle power density. Engineers can tune more aggressively because the emission equipment simply does not need to last as long. So with all these advantages, why do we not just put motorcycle engines in cars? Remember the aerial atom from the beginning of this video? It works because it weighs only 550 kilograms, has no roof, no doors, no radio, and accepts every compromise a motorcycle engine demands. The whole thing looks like a go-kart designed by someone who really hates aerodynamic bodywork. The Caterham 7 Blackbird used a Honda CBR1000RR-R engine to achieve a power-to-weight ratio matching a Bugatti Veyron in a car you could buy for less than a mid-range BMW. The Radical SR3 competes internationally with a modified Hayabusa engine. And back in the 1950s, the BMW Isetta, powered by a 250 cubic centimeter motorcycle engine making just 13 horsepower, actually saved BMW from bankruptcy. But these are track toys and weekend specials, not daily drivers. And the reasons are fundamental. A 998 cubic centimeter sport bike makes about 85 newton meters of peak torque, and it delivers that at 11,000 revolutions per minute. A 2-liter car engine makes 200 newton meters at 2,000 to 4,000 revolutions per minute. Cars need grunt at low engine speed for pulling away from traffic lights, climbing hills, and sustaining highway speeds without screaming at 8,000 revolutions per minute. The Yamaha R1's power delivery has been described as particularly lethargic below 9,000 revolutions per minute. Imagine trying to merge onto a highway in that dead zone. Sport bike engines accept much higher specific stress and operate with far shorter maintenance horizons than car engines. Car engines are built to cruise past 200,000 to 300,000 kilometers without breaking a sweat. At 14,000 revolutions per minute, valves open and close 233 times every single second. The thermal and mechanical stress is relentless. Motorcycle valve check intervals typically fall between 12,000 and 24,000 kilometers. Many modern car engines require no valve adjustment whatsoever for the vehicle's entire lifespan. And the noise. High-revving motorcycle engines in an enclosed car cabin, without the extensive sound deadening and balance shafts that car engines use, would be absolutely unbearable in everyday driving. Add all that isolation hardware, and you have negated the weight advantage that made the motorcycle engine attractive in the first place. Now here's where I'm going to flip this entire story on its head. There is a metric called BMEP, brake mean effective pressure. It measures how much useful work each individual combustion event produces, completely independent of RPM and displacement. Think of it as the true efficiency of each single explosion inside the cylinder. By one commonly cited engineering comparison, the Norton Manx, a legendary racing motorcycle from 1955, achieved a BMEP of roughly 14 bar. A modern MotoGP engine, after 70 years of development, exotic materials, and billions of dollars of research and development behind it, lands in roughly the same ballpark. Yes, you heard that right. In 7 decades of motorcycle racing evolution, the thermodynamic efficiency of each individual combustion cycle has barely improved at all. Most of the dramatic power gains in motorcycle history have come from spinning faster, with improvements in breathing, materials, and engine management helping those engines survive it. The MotoGP engine makes 2.4 times more power than the Norton Manx primarily because it spins 2.4 times faster at 17,000 RPM compared with 7,000 RPM. Mean piston speed only increased from 20 to 25 meters per second across that entire 70 years of development. And here is the real kicker. Many modern car engines achieve BMEP values of 12.5 to 14.2 bar. The Ford 5.0-liter Coyote V8 hits 14.2 bar. That matches or exceeds motorcycle engines on a per-cycle basis. So when people say motorcycle engines are more efficient than car engines per cubic centimeter, that is technically misleading. A sport bike producing 200 horsepower per liter is not extracting more energy from each combustion cycle than a car engine at 100 horsepower per liter. It is simply combusting twice as often per second. The real engineering achievement of motorcycle engines is not better combustion. It is surviving the violence of more than 14,000 RPM through exotic materials, radical cylinder geometry, and ingenious valve train solutions. Every titanium valve, every DLC coating, every desmodromic cam, and every gram of magnesium serves the same goal: spin faster, survive the consequences. That is why motorcycle engineers did not build better explosions. They built engines that survive more of them per second. And honestly, that might be even more impressive. If this blew your mind, subscribe for more deep dives into the engineering behind motorcycles. I'll see you in the next one.